Dear friends, we are here to discuss a simple numerical on how to calculate fan total pressure. So initially, we would be talking about the method of calculating the fan total pressure, and then I would take a small numerical which would explain you this concept better. So let us begin with the methodology as to how do we arrive at the fan total pressure. Look at this beautiful figure. This is the actual ducting system which you find is insulated, and if you want to determine the fan total pressure and hence to select the fan, then we need to do some calculations. The method is we need to break this HVAC duct system into number of small sections, and at each section we need to calculate the different losses. Then we need to add up those losses and find out where the losses are maximum. The length across which the losses are maximum is called as the index run. And that index run, wherever you get the index run, wherever the maximum losses happen, the total length from the fan back to the fan, that index run addition of the losses is the fan total pressure. So for calculating the fan total pressure, as I said, we need to break up the ducting system into small sections, and with the help of small sections we calculate the pressure drops, add up those, and then find out the pressure drops in each run, and wherever you get the maximum pressure drop, that run we consider as an index run, and hence calculate the fan total pressure. And what to do with the fan total pressure? Using the fan total pressure, we arrive at the fan capacity. So what we need to write down when you want to find the fan total pressure is, we need to write down the flow rates, the air flow rates in the main duct as well as in the branches. Then we need to know the cross-sectional area of the main duct as well as the branches. Then we need to know the length of the section, and the velocity of the section can be calculated as Q upon A. Once you know the flow rate and if you know the area of the duct, cross-section area of the duct, we can easily calculate the velocity as Q upon A. And then we need to calculate the velocity pressure. This formula is given for the pressure in MKS unit, but we would be using the SI unit system to calculate the pressure. Okay, so let us begin with the method. Select the fan duct system, do accurate measurements of the length. Then from the manufacturer's catalog, look for the losses which they give for the filters, the dampers, and so on and so forth. Okay, and those losses in filters, dampers are to be taken from manufacturer's catalog, and the other calculations are to be done by using the friction chart and by using the basic formulas for dynamic losses. Okay, if the friction chart is not available, and that is the case if it is not a standard duct, if it is not a standard galvanized duct, then we cannot use the friction chart, or we need to use the friction chart for that non-standard duct, or a better way is to use the basic expression which is known as the Darcy-Weisbach equation for calculating the frictional pressure drop. We know that in the ducts, along with the pressure drop in the filters, dampers, and along with the frictional pressure drop because of friction along the length of the duct, there are other major losses, and they are called as the dynamic losses. And those dynamic losses happen because of elbows, because of transitions, because of T's, okay, and so on. We had a discussion on this, and for that we need to refer to the ASHRAE handbook for finding the dynamic loss coefficients. Okay, so this is how we need to proceed for estimating the fan total pressure. And once you get the fan total pressure, we need to this is how you proceed to calculate the losses. And as I said, we need to then sum up the losses along each run, and wherever you get the maximum losses, that losses we need to call it as a fan total pressure. Okay, so in order now to explain you this calculations, let me share with you this numerical, which would help you understand how this fan total pressure is calculated. Okay, so this numerical, let us read this numerical, what it tells us. So it tells us that a fan's total pressure has to be calculated, and the fan is to be fitted in an arrangement in a duct, in a air handling unit whose dimensions are 90 centimeter by 70 centimeter. Okay, so this is the dimensions given for the ducting which houses the centrifugal fan, housing which has this dimensions 90 centimeter by 70 centimeter, and the flow rate of the fan is also decided, that is, it has to be at the rate of 11.5 cubic meters per second. So this flow rate, how do they calculate? This flow rate is the required flow rate, and this is arrived at by knowing this cubic by doing the load calculations. Okay, so for example, if you want to cool room 1, room 2 and room 3, in that case room 1 would require certain flow rate, room 2 would require certain flow rate, and room 3 would require certain flow rate. So add the 3, and that will give you the total flow rate which has to be delivered by this centrifugal fan in this example. Okay, so this is how this rate, that is Q, is decided. Okay, so Q is given as 11.5 cubic meter per second. Okay, then you know that the fan would have an inlet and fan would have an outlet. Okay, we have discussed this in detail. Inlet means, the inlet to the fan means the return duct, and the outlet to the fan means the supply duct. Supply duct means the duct which supplies the conditioned air from the fan, that is from the air handling unit housing the fan, to the conditioned space. And return duct means the duct which carries the air from the space back to the fan, rather back to the air handling unit. Okay, so inlet duct means the return duct, and the outlet duct means the supply duct. So in this numerical, the dimensions are given of the inlet duct, that is of the return duct. It is given to be 90 centimeter in dia, and the outlet duct is given to be 100 centimeter in dia. Then the inlet duct is 15 meters long, and the outlet duct is 60 meters long. Now we are making an assumption that it is a straight duct, and in actual real life problems, when you want to calculate the fan total pressure, as I said, that duct which is at the outlet as well as at the inlet would have number of turns, bends and so on, okay, depending upon the layout of the building, and it would have n number of fittings. Okay, but because this is the problem just to help you understand and calculate the fan total pressure, I have taken a case where the duct is straight, both the inlet duct is straight as well as the outlet duct is straight. So that way the losses would be minimum because there are no bends. Okay. There is a diffuser, however, diffuser fitting is that because the dia of the fan outlet and the outlet duct is different. So because this is 90 centimeter and the outlet duct is of 100 centimeter in diameter, so we need to have a diffuser like this. So a diffuser like this, okay, where this is 90 centimeter and here it would be 100 centimeter like this. Okay. Then it is given that there is a filter, damping and the cooling coil which is housed in the air handling unit. Okay, and this would encounter a pressure drop. Okay, Okay, as I said, these pressure drops in the filter, damper, and cooling coil are to be obtained from the manufacturer's catalog. Okay, however, it is straight away given in this numerical that this is 15 mm of water column. Okay, uh, because it is a problem, it is given. But if you want to do the actual calculations of fan total pressure, you need to refer to the manufacturer's catalog and obtain this value. Okay, whatever value they give you, that has to be taken as a pressure drop value at the filter, damper, and the cooling coil. Okay, so we will be using 15 mm of water column as our value. Then we know that there would be friction in the outlet duct as well as inlet duct. So in this case, they are straight away given the friction factor. This friction factor has to be obtained again from the standard books, data books. If you want to do an analytical calculations, we can use this value of F from the data book, or you can arrive at the friction pressure drop directly from what is known as a friction chart. So I have done a separate lecture on how to use the friction chart. So we will not be using that method now. We would be using an analytical method, the method for calculating the Darcy-Weisbach equation for calculating the friction drop. Okay, and everything is given that way, and we need to calculate the fan total pressure. So you are required to calculate the fan total pressure. That is the problem. And if you know the fan total pressure, as I said, we can also calculate the theoretical power input to the fan, which is Q into FDP, and you can also calculate the actual power of the fan by incorporating efficiency. So actual power of the fan would be Q into fan total pressure upon the efficiency of the fan, this way. So this will give you the actual power of the fan. So this way, this is very useful sort of calculations. If you appreciate these calculations, then the real life problems also you would be in a position to solve them. Okay, so let us step by step arrive at the calculations. So I had just drawn a schematic of this. So this is the inlet to the fan, which is nothing but the return duct, and this is the outlet of the fan, which is nothing but the supply duct. So this is the supply duct, and this is the return duct. Okay. And this apparatus houses the filter, damper, and cooling coil, whose pressure drop is given straight away. This pressure drop of this is given if this is let us say whatever you call it as, it is given to be 15 mm, not point, it is given to be 15 mm of water column, 15 mm of water column. So this pressure drop is known. As I said, in real life we need to refer to the manufacturer's catalog to arrive at this pressure loss in the filter, damper, and cooling coil. Okay, so now this is calculated. Now we need to calculate the other losses in the duct system. So what are the losses in the duct system? So the losses in the duct system would be the frictional losses. The frictional losses would be what? The friction losses would be in the inlet duct, that is this, and there would be friction losses in the outlet duct. Okay, frictional losses into inlet duct into frictional losses into outlet duct. Now, what is that frictional losses? How do you calculate that? So, that frictional losses is calculated from this relation 4 FL upon D into PV. Okay, into PV. Okay, so this term can easily be calculated now, because what is given to you is the diameter of this. This diameter is given. It is 0.9 meters. It is 90 centimeters, means 0.9 meters. Then this friction factor is also given to you, which is 0.004. Then this length of this inlet duct is also known. For the inlet, it is given to be 15 meters. 15 meters. Okay, and at this section, if we call it as section 1-1, this is section 1-1, you can easily calculate the velocity pressure also. And how do you calculate the velocity pressure? So velocity pressure PV1 is half rho c square, half rho into velocity square, which is coming, if you substitute the value of density, this comes as C1 into 4.04. So this expression you can remember, C square. And if you solve this, now you need the velocity C1. Now how do you get the velocity C1? C1 is equal to Q by A1. Okay, so at the inlet you need to find the velocity C1, which is Q by A1. C1 is the velocity, Q is the flow rate, which is given. How much is that? That is given to be 11.5. And A1 is, assuming this to be a circular duct, pi by 4 d1 square. Okay, and the diameter of this duct is also given. Okay, diameter of this duct is also given. So it is 90 centimeter in diameter. So from that you can calculate the cross-sectional area and pi by 4 d1 square, and that gives you this area. You would get it as 0.636. Okay, and this way you calculate C1. So C1 comes to around 18.1 meters per second, and if you put this 18.1 meters per second over here in this, okay, then you can calculate what is PV1. So this PV1, if you calculate it as C1 upon 4.04 square, okay, that comes as 20.1. 20.1. Okay, and this way you can calculate the inlet duct friction loss. Inlet duct friction loss. The other way is, instead of using this analytical method, you can also use the friction chart for calculating this friction loss. Okay, so I have calculated now for this inlet portion the friction loss. Similarly, at the outlet portion, I can calculate the friction loss. Friction loss. Here the diameter is different. Okay, and this F factor is also different, I guess. Yeah, it is different. So here it is 4 F dash, let us say L dash, D dash for outlet, I am saying, and here we would say PV dash. Okay. So again, the usual method, you will have to find this PV dash by using this C dash upon 4.04 square, and this C dash you have to find by using this flow rate Q. Okay, so that way if you do, you would get this PV dash as 13.14. Okay, same method as this. First we'll have to find C dash as Q upon A dash, where A dash is the outlet. This is dash, I am calling it as dash outlet, A dash. Okay, so using this, Q would remain the same. Q would remain the same. From that you will get the value, and I have got this value as PV dash as 13.14, which you can put it over here. Then again you have this value F dash. F dash is given to be 0.0 something, 0.035 or something like that here. 0.0035, that is this, and this length is 60 meters. This length is 60 meters. This 60 meters in length, so L dash is 60 meters. Diameter is given to be 100 centimeter, which means 1 meter. 1 meter, and this, if you calculate, you will get the friction drop as 11.04 mm. Okay, water column. Now this, you see that outlet would have more friction loss because the length is more, and we are assuming it a straight section. So in the real life, this friction loss would be less, more, because then it would have other losses in terms of fittings and all that. Okay, so friction loss is that friction loss, and if in real life the length is more, this friction loss would be more, right? So this is one calculation, that is, you have calculated the friction loss. The other calculation which is important is the losses. In this we have already considered losses in the filters, dampers, and cooling coil. So this is one, and we have to calculate now the losses in the inlet section, inlet loss. So this inlet would have some losses, and it is straight away given to be 0.5 PV1. Okay, so inlet loss, if I want to write at the inlet loss here, inlet loss is given to be, loss coefficient is given to be 0.5 of PV, 0.5 of PV. So this is 0.5 into 20.1. So this is 10.05 mm of water column. Okay. Okay, so this is the inlet loss. Then what other loss we will have to consider? We'll have to consider the loss in the fan diffuser. Okay, loss in the fan diffuser. So this diffuser, because of this diffusion process, you would have the losses. Okay, and this has to be calculated from the this area and this area from the handbook. Okay, and you will get it as some C naught into PV. Okay, but in this problem, in real life, we'll have to find this diffuser loss by using this area and this area. Okay, and from the friction chart, you'll get this coefficient, and then you'll have to multiply it with velocity per head. However, here it is straight away given as one third of the pressure drop across this. Okay, pressure drop across this. That is, this is 20.4 minus 20.4 minus 13.14. 13.14. Okay, so this 20.4 into, this is 20.4 into minus 13.14 will give you the loss in the diffuser. So this way you have to consider this diffuser losses. Okay, as I said, there would be many losses apart from this, because this is a straight duct. So we have not considered the losses in the elbows. Okay, we have considered only one such loss because of change in area, that is diffuser. Okay, we have considered the losses because of inlet and so on, but actual losses would be much more complicated. Okay, so if you add up this pressure losses, so this pressure losses calculations, if I do, that comes out to be, if you add this entire thing, so you need to add up this 10.05, that is the inlet loss, plus inlet duct friction loss, which is 5.36. You add this, then you have to add this 2.42, which would be the diffuser loss. So this is 2.42. This would be 2.42. 2.42 plus you have this as 11.104, which is the outlet loss, outlet friction loss. Okay, add up this and you'll get a number which is 43.87. 43.87. Okay, so this is a friction loss in the duct system. But friction loss in the duct system is not the fan total pressure. You'll have to add the velocity pressure at the outlet to calculate the fan total pressure. And what is the velocity pressure at the outlet? Velocity pressure at the outlet we need to calculate as, let us calculate that. PV outlet will be equal to V square, V upon, C upon 4.04 bracket square. Now what is the outlet velocity? Outlet duct velocity would be again Q by A, and if you do that calculation Q by A, knowing the area, you will get as 14.64. So if you substitute this 14.64 somewhere here, 14.64 upon 4.04 square, you will get what is known as the PV outlet, velocity head at the outlet, which is 13.14. Okay, so if you add this 13.14 velocity head, then we'll get what is the fan total pressure. So that comes to be, in my numerical, that comes to be 57.01 mm of water column. Okay, so this is how one calculates the fan total pressure. I have taken a very simple example which does not involve the elbows and other fittings. Okay, and I had taken only a single run. As I said, in the real life, we have to take number of runs, and then we need to do such calculations for each run. And wherever you get this maximum FDP, maximum pressure losses, that we would have to consider for calculating the fan total pressure. So fan total pressure is the same calculation, pressure loss calculations in duct systems, but for the longest run involving the fittings and other bends. Okay, so I hope that this concept of calculating the fan total pressure is clear. Okay, have a good day.